Hello, everyone. Today we're going to be talking about earthquakes. So, we'll, quite a little bit to show you here. Some of the main points that I want you to be able to pull away is what are earthquakes, of course, where they happen, um, the anatomy of earthquakes, so what's produced when that rock fails, when it slips very quickly, um, how are they measured, and what else can we learn from earthquakes by what they produce and what we can gain from how they operate. So we're going to get right into it, and we're going to start with just a very basic understanding of what earthquakes are. Earthquakes are natural vibrations of the ground caused by movement along gigantic fractures in the earth. Um, I kind of think of it like stress, stress on a physical object. So, for example, I have a stick here. Um, when stress is applied to the stick, you can see that it bends. Rock operates the same way. If you apply stress to the rock, very slowly over time, the rock can actually bend into form. We've seen that in folding of rock layers in the previous unit. But with an earthquake, so much stress has been applied to the rock that the rock fails. It snaps, and when the rock snaps, it um, produces vibrations in the form of energy in the form of vibrations that can travel outwards in a sphere. Um, Now, earthquakes generally happen within the crust. So, an average thickness of continental crust is about 20 miles, and average thickness of oceanic crust is about 6 miles. 6 miles. So, they happen inside the crust, so they don't happen very far from the surface. But when that rock fails, that energy will spread out in a sphere from all directions. And lots of analogies that I could use here. Kind of like the earth is like a gong or a bell. So when these earthquakes happen, the earth rings, and so that energy will travel outwards throughout the entire planet. Another is in a bathtub, you know, full of water, and you put your hand in and you slosh the water, and you can see the wave as it transmits through the water, and will even reflect off the back and then move backwards and forwards. And also the ripple in a pond. So you throw a rock into a pond, hits the water, and the ripples spread out in all directions. Earthquakes are very similar, except this time it's from the stress overcoming the limit of the rock snaps very quickly, producing energy that spreads out in all directions. But along the surface is where we're really going to be measuring them, but also where we're going to feel the effects. So, where do earthquakes happen? What can we garner from their location? What can we tell about earthquakes based on where they happen? So let's take a look at the map here. You see tectonic plates, Pacific plate, Eurasian plate, Nazca plate, North American plate. We talked a lot about these in the previous section. Take a look at this earthquake monitor. This is live, and it produces little circles anywhere that there's an earthquake on the planet. Today is in red, yesterday is in orange, yellow is in the past 2 weeks. And then the size of the circle denotes the magnitude of the earthquake or the energy release. Purple is in the past 5 years, and they're just represented by dots. But if you look at this, and you can see the majority of earthquakes actually happen along these plate boundaries. In the past 5 years, divergent boundaries, convergent boundaries, transform boundaries as well. Most earthquakes happen along these plate boundaries. So they tend to occur along the boundaries of tectonic plates. Please remember that the crust or the lithosphere is composed of pieces that fit together like a jigsaw puzzle, like a cracked eggshell, a hard-boiled egg. The locations of those earthquakes tell us where those plate boundaries are. So let's talk about a fault. What is a fault? Think of plate boundaries as the big ones, the big regional ones. A fault is just a smaller break in a body of rock where one block slides relative to the other. So there's movement. When the stress on the earth is too much, the rock will crack along a fault and move. A fault is just a break. Please understand that these faults occur on any type of plate boundary particularly convergent boundaries and transform boundaries, but on any type of boundary. A fault is just the actual break in that crust when it moves relative to another piece. There are 3 types of faults based on 3 types of stress. We're going to talk a little bit about each one. First one is called strike-slip fault. And it's the same type of stress as a transform boundary or shear stress. So that's sideways. Probably should do more like this, but sideways motion. The next one is called a normal fault, caused by tensional stress. So in a normal fault, the crust actually moves down. One part of the crust moves down relative to the other. And then a reverse or thrust fault is caused by compression stress. So the rock is being squeezed together, and then the rock will break along that fault line, and one side will move up relative to the other. Let's take a look at some animations for each one. And again, we'll start with strike slip. So again, strike slip faults are just like transform boundaries where they move against one another. Not a whole lot of up and down motion, but slipping sideways. They're caused by shear stress. So strike slip, the rock slips past. So it builds up tension, builds up stress, slip, earthquake. The next one is a normal fault caused by tensional stress, so being pulled apart like a rubber band, being stretched. So in this one, when the rock is pulled apart, you'll see one side slides down relative to the other. All right, so this brings me to an important point. There's some terms called footwall and hanging wall. Here's the easiest way to remember it. The footwall is the one that's shaped like a foot. So you can see here in this little diagram, we have the heel back here, your toes would be over here, kind of shaped like a foot. So it's called a footwall. The hanging wall is the other side. It's the one doing the motion relative to the footwall. In a normal fault caused by tensional stress, the hanging wall drops relative to the footwall. So again, tension, the rock drops, the hanging wall drops relative to the footwall. Compression stress can cause 2 different types of faults, but we'll just kind of group them together. One is called a reverse fault, the other one's called a thrust fault. Thrust fault is just a really extreme form of a compression type fault, but they both operate the same way. So in a compression, it's going to be a normal. In a reverse fault or a thrust fault, a reverse or a thrust fault caused by compressional stress, the hanging wall pushes up relative to the footwall. So again, here's your footwall, the hanging wall slides up along this plane. Same thing with a compression fault, just a little bit more extreme. So footwall down here at the bottom, the hanging wall moves up relative to the footwall. So again, hanging wall, footwall. So here's the footwall shaped like a foot, toes, heel. You'll see here this line, this fault. This is the hanging wall. In this case, it is a reverse fault caused by compressional stress. So when the rock was being squeezed together, it breaks and slides up along that fault plane. So the hanging wall moves up relative to the footwall. So plate boundaries are large scale. Faults happen on much smaller scales. So any one type of plate boundary, transform, divergent, convergent, any one of those can have several different types of faults, all 4 different types of faults. So what's the difference between them? The difference between a plate boundary and a fault is really just scale, just size. So for example, here in California, the most famous fault, strike slip fault is the San Andreas, where on the western side, it's moving down, moving up relative to the eastern side, which is moving slightly in a downward motion. So that is a fault that's located along that entire plate boundary. part of the Pacific plate boundary, which is one of the largest on the planet. So again, faults are just smaller scale, but same types of stress: compression, shear, tension. It's just that in plate boundaries, we call tensional stress, the big ones, divergent, compressional stress, convergent, shear stress, transforms. When we talk about faults, normal faults are divergent or being pulled apart in tension. Reverse and thrust faults are compressional stress, and then strike slip faults are your shear stress. So let's take a look at some examples of each type in the real world. Strike slip fault. This is with ground rupture. You don't always see this, but with this strike slip fault example, the ground actually ruptured. So one side of this ground rupture moved in one direction, where the other side moved in the opposite direction. In 1906 in San Francisco, there was quite a large earthquake. And you can see in this picture where this fence actually used to be connected. So get that sideways motion. You can see the ground rupture right through the middle. Again, you can see the line here, the crack in this old barn. Normal fault caused by tensional stress means that the hanging wall drops. And so on this picture on the right-hand side, you can see these people here. Sorry, it's not very clear. This person standing at the top. This side over here on the left actually dropped relative to this side on the right. And you can see this whole fault plane is actually viewable right there. So just drop down very quickly. On the picture on the left-hand side over here, the opposite is still a normal fault, but the side of the house actually dropped relative to the other side. All right, a reverse fault, again, is caused by compressional stress. And here we can actually see the fault line. And you can see where this side, the hanging wall side, the side on the right, actually pushed up relative to the footwall. Again, looks like a foot, put your toes here. So this side actually pushed up, and you can actually see where the line of the sedimentary rock when it was laid down right there. Thrust fault is just an extreme reverse fault. And this one is kind of neat because you can actually see the rock had deformed for quite some time before it actually slipped along the fault plane. So here's that deformation, that curve, here's your fault line. That's where it was originally. So again, earthquake occurred when this slipped up. Compressional stress, thrust fault. This is a pretty short video. Oh, this is an 8-minute one. So at this point, if you want to watch the earthquake faults, plate boundaries, and stress video, please be my guest. It's about 8 minutes, but it compares faults to plate boundaries and talks about the stress for each one: tensional, compressional, shear. Some relationships, basically the anatomy of earthquake. Where that rock fails at depth, however many miles or kilometers down it is, the exact point where that break happens is called the focus of the earthquake. All right, so it's the focus, it's the point underground. That energy will spread out in all directions from the focus in a sphere. Now, the point on the surface directly above the focus is called the epicenter. When we're talking about damage, the damage will seem to radiate out from that epicenter. Think of epi like epi means, I think, surface. So like epidermis is surface of skin. The epicenter is the center on the surface of the planet, right above that focus, where all the energy seems to spread out, just like the pebble in a pond, the ripples spreading out. The fault is actually the physical crack created when that happens. So if we're talking about a reverse fault, the fault would be the line that's created when that rock fails. So again, focus, the point on the ground. Here we have a normal fault. So we have this side dropping down due to tensional stress. Here's a footwall, hanging wall drops down. Where that crack actually happens is called the focus. The point on the surface directly above is called the epicenter. By the way, oops, real quick way of making a waterfall. So again, at the top will be the epicenter, right directly above the focus. Every type of earthquake generates seismic waves. This is very similar to what you learned about sound waves in physical science. These vibrations travel out. It's a form of energy in all directions, just like in sound, just like the pebble tossed in the water. Each earthquake generates four types of waves, four main types of waves. There's others as well, lots of them, but four main types of waves in two main categories. Those two main categories are called body waves and surface waves. Body waves travel through the body of the planet, the entire Earth. Surface waves, only on the surface. Body waves, the two main types are called primary waves or P waves, and then secondary waves or S waves. The surface waves, I'll kind of just lump them together. I'll talk about them independently right now, but after this, we'll just refer to them as surface waves. But surface waves come in two main varieties as well. They're called Love waves and Rayleigh waves, named after the seismologists who studied them. So Love waves is a side-to-side motion, whereas Rayleigh waves are a rolling motion, much more like an ocean wave. So we're going to look at each type. Let's start with the body waves, primary waves. Things that you have to remember about primary waves. Primary waves squeeze rocks in the same direction that they're traveling. If you remember back to your definition of a compression wave, particles move parallel to the direction of wave energy. So imagine a slinky, push on the slinky on one side, and the energy will travel in that same direction through the slinky. So in this little video here, I'll play it a couple of times. So primary wave, the wave energy travels in the same direction as particle motion. Again, it's just like pushing on a slinky. Wave energy just travels in the same direction. It's compressional wave. They are the fastest wave. That is very important. Primary waves are the fastest wave when it comes to earthquakes. All right. Again, they're body waves. They move inside the body of the planet. Secondary waves are the second fastest. Now these move perpendicular to the direction of wave travel. So imagine this time stretching out a slinky, you move up and down like this, and the wave energy travels. It's kind of like a hump that moves in that direction. So let's take a look at the quick animation here. Again, imagine taking a slinky, whipping it. So an S wave, particle motion moves up and down while the wave energy moves forward. So the big thing to remember here is that they are the second fastest. Primary waves are the fastest. Secondary waves are the second fastest earthquake wave. They also move through the body of the Earth. Last big thing on secondary waves, please make sure you remember this. Primary waves can travel through solids and liquids. Secondary waves can only travel through solids. So primary waves can go through both. Secondary waves can only go through solids. They cannot go through liquids. It becomes very important in just a little while. So primary wave is the fastest. Compression wave go through solids and liquids. Secondary waves, like the whip, second fastest and can only go through solids. Again, the last one are the surface waves. It's the second main category, and there are two main types of waves, but we'll just talk about them in general. So surface waves, surface waves are the slowest, but they're also the most damaging, the most powerful, the most destructive. They only travel on the surface of the planet. They move like an ocean wave, but they also move like a snake, side to side motion and rolling motion. Again, they're made of, it's basically two waves traveling at the same rate, but two different types of motion. So love and then Rayleigh. But both of those motions are combined. That's what makes them so powerful and destructive. They only travel on the surface, but they are the slowest and most powerful and destructive.
The concept of a seismic shadow zone as a global effect of an earthquake is an oversimplification that ignores a broad array of refracted, reflected, and diffracted seismic waves that propagate through the Earth. For now, we'll just focus on direct compressional P and shearing S waves. These are the body waves that take the most direct routes within the Earth and do create shadow zones, which are useful for teaching Earth structure. An earthquake, depicted here at the top of the globe for convenience, sends compressional P waves in all directions, refracting along boundaries with depth, causing curved paths. At the core mantle boundary, they are refracted or bent inward and slow down in the liquid. It's this refraction that causes a shadow zone between the angular distances from 104 to 140 degrees from the earthquake. S waves travel along the same path as the P waves, but at slower velocity because they travel in a shearing motion, perpendicular to the direction of travel. It is because of this shearing that they are stopped entirely by the liquid core. This creates an even broader shadow zone everywhere beyond 104 degrees. It was this lack of S-wave arrivals and recognition of the slowing of the P-wave velocity that caught the attention of seismologists in 1910. By understanding how energy is refracted by different materials and pressures, it enabled them to deduce a liquid outer core. By 1913, the P-wave shadow zone between 104 and 140 degrees was refined to define the core mantle boundary. Remember, these show just two of the types of seismic waves that migrate away from an earthquake.
That gets us into the next section of material, so we're not going to go there yet, but please understand primary, compression, fastest, go through solids and liquids. Secondary, second fastest, cannot travel through liquids. And then surface, only on the surface, slowest and most damaging. All right, so next, what controls the level of shaking? In other words, how big is an earthquake? How do you know how big an earthquake is, or how do we measure them? So there's three things that kind of regulate the level of shaking. And the first, of course, is the magnitude. The bigger the earthquake, the more energy released, the higher the magnitude. You'll hear numbers coming up called the Richter scale. And the Richter scale is a scale that we use to measure the strength of earthquakes based on the amount of energy released. And so the higher the energy, the more the magnitude. The second is distance. As you get further away from the earthquake, the shaking becomes less. And so the energy that you feel will become less the further away you are. I like to think of this as in terms of a star. You can have a really big, bright star, but that's really far away. And so it's not very bright in our sky. Whereas you can have a really dim star that's really close and appears very bright. So the magnitude is the actual measure of the earthquake's energy, but it can decrease with distance. The local soils also have an effect on what you feel from an earthquake. The composition can amplify an earthquake, or it can even reduce the amount of shaking. It just really depends. And there's a special case, something called liquefaction, that can occur with saturated soils, where soils are have lots of water content. So liquefaction can occur with saturated soils. If you get a chance, watch this video of an earthquake that was taking place in Tokyo. The observer really didn't know what was going on and why he was seeing a lot of the water, but we come back to liquefaction later on in the lecture. Make sure you watch this video; it's pretty interesting. Maybe it'll make more sense. All right, so magnitude of an earthquake is the intensity or strength of an earthquake, and it's measured in two main ways. And we're going to get further into these, and you can do your own research as well. First one's called the Richter scale. It measures the amount of energy that an earthquake releases, the actual energy. The thing about the Richter scale is that each number of magnitude is 10 times stronger than the number below it. So going from a magnitude 1 to a magnitude 2, it's 10 times stronger. From a magnitude 2 to a magnitude 3 is 10 times stronger. But that means from magnitude 1 to 3 is 100 times. From 1, 2, 3 to 4, that's 1,000 times. 5, 10,000 times, so on and so forth. So when you get up into those high numbers, 5, 6, 7s, 8s, you're talking about a lot of energy. The higher magnitude numbers don't happen as often. The higher up in magnitude you go, the less frequent they are. So magnitude 1s, 2s, all the time, every day. Magnitude 7s and 8s, pretty rare, pretty rare. They can happen, of course, and they can happen in some very bad places where they're populated. But again, we measure the energy of the earthquake in terms of magnitude on the Richter scale. And it's very empirical. It's based on actual seismograms. It's looking at the amplitude, basically, of the wave on a seismogram. The other way to measure an earthquake is more the touchy-feely method. It's an older method. It's called the Mercalli scale. And the Mercalli scale really is just a ranking of what people experience during the earthquake. And so it measures damage, but from the perspective of people. So it's basically a range of Roman numerals, 1 to 11 or 1 to 12. And it's based on qualitative data, like how much damage was there to buildings? Did chimneys collapse? Did hoses burst? Did fissures open up in the ground? It's how they experienced the earthquake. The funny thing is using both of these methods, either measuring it empirically with a seismograph, where it actually looks at the amplitude of those waves, that can help you pinpoint where the earthquake actually happened. But so can the Mercalli, especially if they happen around people. You can use the Mercalli scale to pinpoint pretty close to the epicenter of the earthquake. We'll get into that a little bit more later. I just want to introduce both of those scales. The quantitative method, the Richter scale, versus the qualitative method, the Mercalli. So let's talk about Earth's structure and what earthquakes can tell us. So primary waves can travel through solids and liquids. Secondary waves can only travel through liquids. So, and remember what I told you about the Earth ringing like a bell or a gong. As those earthquake waves pass through the interior of the Earth, what we found is that some waves can travel through the entire planet. They may refract, change speed, change direction, and all of that information can tell you about the internal structure of the Earth. Earthquakes are like a sonogram, looking at a baby before it's born. You can tell so much information about the baby just by using those sound waves and how quickly they bounce up. In this case, we're not using sound waves, we're using primary and secondary waves as they travel through the body of the Earth and what all of that can tell us. Here's the scheme. Primary waves travel through solids and liquids. When an earthquake happens, primary waves travel through the Earth with some change in speed. This behavior explains the presence of a core. So here's an earthquake, for simplification at the top. You see the primary wave travels through the planet. It's the fastest wave. Notice what happens when it hits this boundary. It refracts, it bends, it changes speed, and then changes speed again after it leaves that point onto the other side of the planet. Also notice because of that bending, there is a shadow zone where no primary waves are received. And I think it's from, I can't remember, 104 degrees to 140 something degrees. But there's a shadow zone on both sides of the planet where no primary waves are received from that earthquake. This tells us that there is an object, and pretty precisely too, based on the the degrees of the shadow zone, the size of that object. There's an object in the Earth that causes these primary waves to change. It explains the presence of a core. Secondary waves can only travel through solids. So when an earthquake happens, now we get this huge shadow zone on the other side of the planet where no secondary waves are received. They're blocked by Earth's outer core. The outer core, turns out, has to be a liquid because these secondary waves stop. That also means, and this is more reinforcement, that the mantle is solid. Secondary waves can travel through the mantle. They cannot travel through the liquid outer core. The mantle is solid, but it acts like a liquid because of convection currents. There is motion there, but it's more like a non-Newtonian fluid or like silly putty. But secondary waves basically show us that there is a liquid portion of the Earth, and that is our liquid outer core. Whereas primary waves and their change in speed lets us know that there's a liquid outer core, but also a solid inner core. So again, these earthquake waves, even though destructive, tell us about the interior of the planet.
The concept of a seismic shadow zone as a global effect of an earthquake is an oversimplification that ignores a broad array of refracted, reflected, and diffracted seismic waves that propagate through the Earth. For now, we'll just focus on direct compressional P and shearing S waves. These are the body waves that take the most direct routes within the Earth and do create shadow zones, which are useful for teaching Earth structure. An earthquake, depicted here at the top of the globe for convenience, sends compressional P waves in all directions, refracting along boundaries with depth, causing curved paths. At the core mantle boundary, they are refracted or bent inward and slow down in the liquid. It's this refraction that causes a shadow zone between the angular distances from 104 to 140 degrees from the earthquake. S waves travel along the same path as the P waves, but at slower velocity because they travel in a shearing motion perpendicular to the direction of travel. It is because of this shearing that they are stopped entirely by the liquid core. This creates an even broader shadow zone everywhere beyond 104 degrees. It was this lack of S-wave arrivals and recognition of the slowing of the P-wave velocity that caught the attention of seismologists in 1910. By understanding how energy is refracted by different materials and pressures, it enabled them to deduce a liquid outer core. By 1913, the P-wave shadow zone between 104 and 140 degrees was refined to define the core mantle boundary. Remember, these show just two of the types of seismic waves that migrate away from an earthquake.
So it really is a simplification, but we have to crawl before we can run. Primary and secondary waves just tell us about the core, the outer liquid outer core, the solid inner core. There are other subtypes of primary and secondary waves or other waves that get into a lot finer detail. But for right now, just understand that primary and secondary waves tell us about the core. So I want to just very briefly show you some of the results of an earthquake, some of the effects. So one of them that I alluded to earlier was something called liquefaction. Liquefaction is where the ground can kind of revert to a liquidy type state because of the intense ground shaking. If there's a lot of water content in the soil, the earthquake waves can actually cause it to behave like quicksand. And that's what you see in this picture from an earthquake that happened in Japan in 1964. These apartments, condos, whatever they were actually built on land that had been reclaimed from probably a wetland, filled in. The water content was still there. When the earthquake happened, it actually caused the buildings to sink. And that's why they look all kind of crazy.
On June 7th, 1692, the Jamaican city of Port Royal, a notorious pirate haven, sank into its own harbor. This disaster, or blessing depending on who you ask, was caused by liquefaction of the ground following a major earthquake. And we know it happened at exactly 11:43 a.m. thanks to a pocket watch that went down along with 2/3 of the town and over 2,000 people. Liquefaction happens when waterlogged loose soil, we call it sand, turns into quicksand, temporarily. If you look closely at sand, you'll realize that it's actually comprised of tons of tiny rocks, and their roundness and roughly uniform size mean there's space between them that can get filled by water. When we step on saturated sand at the water's edge, it's fairly stable because the particles get pushed together and rest on each other, while any excess water escapes by flowing away to where the pressure is lower. We can and do build buildings on wet sandy soil, since the weight of the grains and the friction between them makes the soil behave as a solid most of the time. But in an earthquake, soil particles repeatedly jostle back and forth so much that the water can't flow away. Loosely packed, dry soils tend to compress under stress, but with incompressible water unable to escape the gaps between grains, the soil can't compress and the water takes the load. Unfortunately, water as a liquid doesn't have much structural integrity, so if the saturated soil is forced to compress too much too quickly, it'll start to act like a liquid, and dense objects resting on the now liquefied soil will sink. You can experience liquefaction for yourself in the water-soaked sand near the edge of a beach. It feels pretty solid if you stand still, but if you wiggle your feet, the movement causes the sand to liquefy beneath you, and you start sinking. On a larger scale, earthquake-induced liquefaction can swallow cars, roads, and even enormous apartment complexes. In other words, earthquakes can create quicksand, except that when the shaking stops and the soil particles are no longer suspended in water, the ground solidifies again, and anything that sank becomes stuck, which is what happened to this car.
Crazy. Really neat effect. Or some of the other things, ground shaking. In this example, you see the Colosseum partially collapsed. Anything that's not bolted down or secured to a wall can come off the wall. Cabinets can open, along with refrigerators and just about anything else. This is actually from an earthquake in California in 1994. Pretty high, relatively high magnitude. I think around a 6, maybe 6.5 magnitude. Loma Prieta, California, in 1989, also very close, a little, maybe a 6.5, right outside of Los Angeles. And you can see this highway pancaked. Kobe, Japan, a very similar sized earthquake in 1995, and you can see this whole face of this building just sheared away. Again, remember, surface waves, slowest, most destructive, side-to-side motion, but also a rolling motion. So those two are combining. High enough magnitude, high enough energy can be quite damaging. This building actually used to have another floor. Again, pancaking. Surface faulting, it's where the ground faults very quickly. You can see where this highway just kind of shifted due to an earthquake in 1992. Another effect can be landslides. If you have loose soils on the side of a mountain during an earthquake, the structures that are built on the side can actually slide down. Right, so that's basically it. So we talked about, what have we talked about? We defined what faults were. We looked at the anatomy of an earthquake, focused on the epicenter. We looked at the different types of waves, body and surface waves. Body waves, PNS waves, travel through the body of the earth. Primary waves are the fastest, go through solids and liquids. Secondary waves are second fastest, only go through solids. And then surface waves are the slowest and most damaging. Looked at the 3 different types of faults. Normal faults caused by tensional stress, where the hanging wall drops. Reverse and thrust faults caused by compressional stress, where the hanging wall moves up. And then strike slip faults caused by shear stress, moves sideways. So we'd like for you to take some time and just explore. So this link is to the USGS, U.S. Geological Survey's earthquake monitoring site. It's really neat, really powerful. I'll show you exactly how it works. It's very straightforward. It automatically updates. This is live information. So it's too much information. We're going to zoom in a little bit. So the plate boundaries are actually highlighted in red. So you can see, again, most earthquakes happen along those plate boundaries. You can change the different filters. Here's the key. In the past hour is in red, and the day is in orange, weeks in yellow, month is in white. And then the size of the circle denotes the magnitude. All right, so let's look at 7 days, 4.5 magnitude and up. You can see there's been quite a bit of action. I'll show you this one that caused some people to worry last week. Zoom in. This is the Aleutian Islands, of course, right off the coast of Alaska. Oh, by the way, what is that right there? If you said a trench, deep sea trench, you got it. So here we have the Pacific plate on one side and the Eurasian plate up here to the north. This oceanic plate is older, colder, denser. It's subducting back into the mantle, creating volcanic islands, a volcanic island arc right there. Again, this is because this is a convergent boundary, some of the worst earthquakes can occur because as subduction is happening, it's building up that stress, crack, fault, earthquake. So if you look here, earthquakes don't happen typically all by themselves, especially the larger ones. So as one part of a fault can release that energy, it puts stress on another part of the fault, which can then break again. They're called asperities, but as pressure is released on one part of the fault, another part can slip. So anyway, this is the earthquake I want to show you. This is a 7.6 magnitude, and it had some warnings with it. There was a tsunami warning. I don't think everything ever came of it. There's different links here. This one here called Did You Feel It? Is basically like the Mercalli, has a shake map, so it goes into more detail about the ground shaking. So anyway, just wanted to show you that. But you can also change the filters depending on however much information you want. You can go to different parts of the planet and look at past earthquake activity. Anyway, just play with it, see what you find. See if you can find something interesting. See if there's any within the past hour. Yeah, there's a little one in Hawaii. It looks like a 2.4, 1.6 in Nevada, 1.3 in California. So anyway, very powerful site. Gives you lots of cool information. Last but not least, would like for you to go to the following website. It's a class zone, basically very similar to what you've done before with Grand Canyon. Just basically read through the interactive investigation. How do we know about layers deep within the earth? There's just a couple of questions in the graphic organizer for you to answer, but it's very straightforward. Yeah, just basically a little quick interactive reading. And that's about it. So I know we've gone over a lot. As always, if you have any questions, please let me know. We'll do some things in class to kind of help reinforce. But if you have any questions, please let me know. I'd be glad to work with you. Thank you so much, and enjoy your day.